Hi everyone, and welcome to our video on trig ratios of special triangles. Special shout out to Michael Cheng who made that wonderful intro video. I love it. Without further ado, let's get started. So if you recall, we learned about two special triangles earlier in the year in our similarity unit. And the way we derived them is we started with a square, okay, of side length x. And we said if we cut this square down its diagonal, we could actually examine a right triangle that has the angles 45, 45, 90. And what we realized is that if these two side lengths were x, we could use Pythagorean theorem to say that the hypotenuse is root 2x. And so in that way, we figured out that the ratios of sides are x to root 2x, or in short form, we usually say 1 root 2. So that was our first special triangle. Our second special triangle came from slicing up an equilateral triangle. So what we did is we started with an equilateral triangle, which we know has three angles of 60 degrees, and what we did is we sliced it this way. So our new triangle looks like this. So we know the angles of this triangle. This one is still 60, but this one is 30. And we said that because we kind of know where we were going with this, we were going to label all the sides of this equilateral triangle 2x, making the base of this triangle x and the hypotenuse 2x. And what we did again was we used Pythagorean theorem to get root 3x. So we call this a 30, 60, 90 triangle. And we know the ratios of sides of this triangle are x to root 3x to 2x, or 1 root 3, 2. So why does this, oh, and by the way, I just want to remind you that this triangle, although it is kind of neat in that the side lengths are integers, this is not considered a special triangle because the angles end up being very ugly. Okay, so how does this help us solve these problems? Well, what we're going to be asked to do when given a special triangle, and when we're asked to find the trig ratios, there are two things. Number one, we're not supposed to use a calculator for these. And number two, our answers need to be exact. Okay, exact meaning no decimals, and we can do that if we have a special triangle. So for example, if I look here at what's called number 8, what I can do is I can compare this to a special triangle that I know, and then using similarity styles that we learned previously, we can actually solve for missing quantities. So in my 30, 60, 90 general triangle, I know this is 1, root 3, and 2, and now I can just use comparisons of ratios of sides to solve this. So for example, I can say that x over 1 equals 6 over 2. So x over 1 equals 6 over 2. And it becomes very easy. So I get x equals 3. Okay, similarly, no pun intended, if I have y over root 3, 6 over 2, I get y equals 3 root 3. Okay, so no decimal required, no calculator required. We can just solve these sides. All right, let's look at the next one. Okay guys, so just something to note, I don't want any radicals in the denominator. If you get a radical in the denominator, you need to rationalize it by multiplying by root 2 over root 2, for example, in this case. So you just look at what the denominator is and multiply by that. Okay, so let's look at number 2. This one's a little bit different, and you need to know something in order to do this question. So you won't see it much in grade 10, but in upper years, you will see this a lot more. What does sine squared x mean? Well, what this is actually is sine x all to the power of 2. So textbooks save ink by just taking the 2 and actually just putting it there instead. But what this actually signifies is sine x multiplied by itself 2 times. Okay, so if I want to evaluate sine squared 30, the first thing I need to do is figure out what sine 30 is. And then I raise it to the power of 2. Okay, so if I have 30 and 60, 1, 2, root 3. Well, I know sine of 30 is opposite over hypotenuse. And I know cos of 30, oops. I know cos of 30 is adjacent over hypotenuse. Okay. And we get a nice and neat number. For this one, I can still use this triangle over here. I know that sine 30 is 1 over 2. I know that tan 60, so if I take, this is my reference angle, I get opposite over adjacent. And then let's just have a quick look here at cos 45. Okay, so if I have 1 root 2 and I take 45 degrees, get adjacent over hypotenuse, which is 1 over root 2. Okay, so I multiply all the numerators together, I multiply all the denominators together. I don't like that rational in the denominator, so I'm going to multiply by root 2 over root 2. So we end up getting root 6 over 4. All right, so solve for theta. Do not use a calculator. And I want you to justify your answer using drawings of triangles. So basically, I mean, we probably know this, but that's not enough work. So what I'd like you to do is, what I want you to do is draw out the triangle that you are referring to, okay? So we know, obviously, that if I have the opposite and adjacent side, I know that the ratio of 1 means that they are the same length. I know I'm dealing with a 45, 45, 90 triangle, but I would like you guys to draw me the picture, because remember, we're not using a calculator, so you can't just say tan inverse of 1. Okay, so for me, this is enough. Tan 45 degrees equals 1 over 1. That's a good check. Okay, so cos of theta. Okay, so if this is theta, and I know cos is adjacent over hypotenuse, so I'm going to put 2 on my hypotenuse side, and root 3 is adjacent. Okay, I can see this is a 1, 2, root 3, and because I've memorized the triangle, I know that theta must be 30 degrees. Okay, and yep, you can use your calculator to check, but if we were in a regular class right now, I'd be giving you a quiz with no calculator, so it's really not necessary, but you can convince yourself that this is true. Okay guys, there is some homework for this, and I will see you in class on Wednesday.